Okay, so we're looking at a single phase, one phase, 230-volt motor, and it's got a 5 kilowatt rating and 28 amps from supply. So our first question is, what is S equal in kVA? Now, this one's a relatively simple one. We just go 28 amps times by 230 volts, because the formula we're using here is VA equals V times A. So 28 amps times 230 volts, put that in our calculator, 28 times 230, and we get 6,440. 6,440. We move the decimal place 3 to the left, turn it into kVA, so we get 6.44. Now, our next question is, what is the power factor? So we draw our triangle. So we've got horizontal line, 5 kilowatts. We've got our kVA, which is 6.44. This will be our VAR for later, and this is our theta, which is our power factor angle. However, we don't actually need this triangle yet. One of the things to remember is power factor will always be 1 or less. The reason for that is the watts line and the VA line. If power factor is 1, is the same. If it is less than 1, the VA gets bigger. So you can always remember the order of this, whereas power factor equals, and then it is watts over VA. So in that case, it equals 5 over 6.44. Therefore, our power factor equals 5 divided by 6.44, 0.776. So rounding that up, because our last digit is a 6, becomes 0.78. So we now have our triangle for our power factor for part B. Next, they want to know the phase angle. So we've got our triangle once again, drawing it, so we've got 6.44, 5, unknown, and they want to know this angle here, which is theta. So our theta formula, we use A over H, because cos theta equals A, which is the adjacent side to the angle, not the opposite, which would be on that side, over our hypotenuse. So that equals equals 5 over 6.44. Same thing that it was with our power factor. We need to actually work out, we need to work out the angle. So what we actually end up with is theta equals cos to the minus 1, 5 over 6.44. As we know from earlier on, that was 0.78. So cos minus 1, 0.78 equals, and let's put that in our trusty calculator, cos, and then 0.78, and we get our 38.739 degrees. Now, because that's a 9, we're going to round up in this case, so 38.74 degrees. Next one, we're wanting cos of theta 2 equals 0.9. So it's a simple matter of going theta equals cos minus 1, 0.9 equals, so cos 0.9 equals, and we get 25.84. 1, which being a 1, we'll round down, so equals 25.84 degrees. Our last question is find out the Q required. So we have our triangle. It has our 5 kilowatts. Being that this is a motor, it's actually an inductive load, so the triangle should technically be going this way because it's a lagging power factor. And we know we had a 6440, and we want to make it more efficient. We're improving the power factor. So we're going to have a different line there. The angle here is the one where we've already worked out our cos theta, which was working out to be 25.84. And our theta for there was our 38.74. And they want to know this value here in kVAR. And we know this value here already. Or we don't know, but we can calculate it, I should say. Now, there's a few ways to do this. One of them is using the actual power factor value to get this value and use Pythagoras. So if we start with that method, we have 5 kilowatts, and that's what I write out the formula. P dot F equals our watts over our VA. Now, we have 0.9 for our power factor equals, the watts never changes, it's our 5,000, over our VA. Now, we don't know our VA. We can swap these two values with our quick rearranging, so we end up with VA equals 5,000 divided by 0.9. VA equals, now 5 divided by 0.9, 5.555 VA, kVA. I should have had a decimal point and all of that. So being that it's a 5 there, at the end it actually was 5.6, so 5.56 V kVA. Sorry, a bit messy. So that's our value along here, 5.56 kVA. And our previous value here, we already knew is 6.44 kVA. And we could use Pythagoras to calculate this length here and that length there. So with Pythag, we have our VAR equals, or our Q equals, the square root of square root of S squared minus W squared. So in this case, VAR equals our S squared, which is our 6.44 squared, minus our 5 squared. So VAR equals, we get our 6.44 squared minus 5 squared equals, and then we get the square root of that. And we end up with 4.058, so rounding up to 4.06 VAR. So that is the total, 4.06. Now, this value here, we can also work out by doing the same figures, which is instead of 6.44, we're now using 5.56. So 5.56 squared minus 5 squared square root of that equals 5.56 squared minus 5 squared equals, and then shift square root, shift answer, 2.431. So 2.43. So we know this value here is 2.43. 4.3. To work out this value here, we get this value, we minus that value, and we'll end up with that value. So 4.06 minus answer, and we have 1.628, so 1.63. And that would be the most accurate way to get the answer. So our final answer for this is 1.63 kVAR. Lots of hard work, and you end up with the most accurate answer. Now, there is a second, easier and faster way to do this calculation, and this is the one that they're actually expecting you to use. Where'd my information go? This is a formula that we don't use very often, but you will have seen if you look in the aspect formula sheet, which is QC equals P tan theta 1 minus tan theta 2. So the way you would work this one out, oh, that's a Q, is QC equals, our power was 5 kilowatts, so 5 times, and then in brackets we have our tan theta 1 was our 25.84 degrees. No, whoops. Meant to use the bigger one, so 38.74. Not a formula I use very often. QC equals 5 times tan 38.74 minus tan 25.84, close bracket. So if we get our calculator and we go tan 38.74, and we will get 0.802, so 0.80 minus and our tan of 25.84, and we get 0.484, so 48, rounding off, and we have 5 times that. So 5 times 0.8, make sure you put it in brackets. You need to do this minus before you do the multiplication, otherwise you'll have issues. The tan is a multiplication inside the black bracket, essentially. So that happens first, then the negatives happen. So you can put it straight in your calculator, tan 0.8 minus tan 0.48. Tan 38.74 minus tan 25.84, and we get 0.318. We get 5 times answer, and we get 1.59 kVA. Now, the reason why this is different to our previous one is, which was 1.63 kVA. They are very similar numbers. When we're doing this, tan is using the opposite and the adjacent, and it's relying on this angle here. Now, a very subtle difference in angle would actually have a large impact on the size. And what that means is this changing angle will have a drastic impact on this line here of its length. And that is why the first method was more accurate. The second method was using rounding values, but they were used in the quiz. already, so they're expecting you to carry on from those answers. So if you actually did it the Pythagoras method, you would get marked wrong. If you did it using the faster method, you would be marked correct. However, this method can be done with full accuracy, providing you don't round in the first place. So may as well test that out, because we've got our values here of 5,006,440, and we've got our existing power factor, and then we can throw in our new one, which is going to be 0.9 when we do the cos theta on it. So going into our maths, we end up with 5 divided by 6.44, and then cos to the minus 1, now 5 over 6.44 equals our theta. So shift cos shift answer, and we've got our theta, and then we can go minus, and you'll notice to start with that's already 39, not 38.74 for our rounding. So minus, and we're going to do our cos minus 1, 5 over 5 divided by 0.9, because that's our new cos theta, for our calculating our VA. So we have minus close bracket, that's to get our we will actually end up with an answer tan shift answer. So an answer equals minus, now I can bring my next value, tan, so answer minus tan, and then in that tan we're going to have shift cos, and then we've got new bracket 5 divided by new bracket 5 divided by 0.9, close bracket for that bracket, close bracket for that bracket, close bracket for that bracket. And that gives us our 0.327. And then we do our 5 times shift answer, and we get 1.637, just rounds up to a 1.64, which I mustn't have rounded up with my first one, but ends up with a much closer and more accurate answer because I didn't round. Hopefully that is helpful for that question. The next one you were having issues with was to do with burden. Pull up my emails. I will have a better view of the question. So we have a large industrial estate supplied by 1,000 amp supply transformer. It is currently drawing 800 amps. So we've got 800 amps flowing, and we've got 1,000 to 5 current transformer, so CT. What that means is we're only actually using 800 of the 1,000 it can measure. So we would actually multiply it maintains the same ratio. So we would end up with 4 amps. So if we had 1,000 amps flowing, we would have 5 amps. If we've got 800 amps flowing, we have 4 amps on the current transformer. So our formula is power equals I squared Z, which is our burden, which we actually measure in VA because it's total impedance that we're working with. So VA equals our I squared is 4 squared times by, and we've got a impedance and a resistance, and they get added together. So we've got 0.3 ohms for the meter and the equipment, 0.2 ohms. So what we end up with here is VA equals 4 squared, which is 16, times and then 0.5, which is another way of dividing it by 2. So VA equals 8. That would be the answer to your burden question. Hopefully this has been helpful, and good luck with it later on.
You're right.